Welcome to Bot Thoughts by AmtocSoft. I'm Alex. Sam is with me. Today we're talking about memory, specifically, why AI agents forget everything the moment a conversation ends, and what you can actually do about it. Memory is the difference between an agent that's useful once and an agent that gets better every time it runs. Sam, start with the bad news. Why do LLMs have such terrible memory by default?
The core problem is architectural. Large language models process text one context window at a time. Everything the model knows for a given conversation is what's currently in that context window. The moment that window closes, nothing persists. The model doesn't learn from the conversation, doesn't remember the user's preferences, doesn't carry forward any state. It's stateless by design. The same model weights serve every user of every conversation, and those weights change only during training, not during inference. So an agent built on a raw LLM has exactly the memory of a goldfish. You can extend the context window. GPT-4 has 128K tokens. Gemini goes to 1,000,000, and that helps for within-session recall. But even a 1,000,000-token context window has limits. It's expensive, it degrades attention quality on very long inputs, and it solves zero of the across-session persistence problem.
So how do practitioners actually solve this? Are there different types of memory for different purposes?
There are 4 distinct types, and they map loosely onto human memory psychology. In-context memory is everything currently in the context window, fast, immediate, but ephemeral. Episodic memory is a store of past events, specific conversations, specific actions the agent took, specific outcomes. When the agent needs relevant past experience, it retrieves relevant episodes and injects them into context. Semantic memory is structured knowledge. Facts, preferences, user profiles, domain knowledge. This is more like a knowledge base than a diary. It stores what the agent knows, not what it did. Procedural memory is the learned patterns for how to do things well, successful tool call sequences, prompt templates that worked, workflow patterns that reduced errors. Each type is stored differently, retrieved differently, and useful for different agent behaviors. A well-designed production agent uses all 4.
Vector stores keep coming up in memory discussions. What role do they actually play here?
Vector stores are the retrieval backbone for episodic and semantic memory. Here's how it works. When the agent has an experience worth remembering, a conversation that resolved well, a fact the user stated, a useful tool interaction, you embed that experience into a vector using the same embedding models used for RAG and store it with metadata. Timestamp, conversation ID, topic tags. When the agent needs relevant context for a new task, you embed the current query, do a similarity search against the stored vectors, and retrieve the top K most relevant memories. Those retrieved memories get injected into the system prompt or the user message before the LLM call. The LLM sees them as context, not as memory in any special sense. They're just text. The intelligence is in what you store when you store it, and how you query. Popular options are Pinecone, Weaviate, Chroma for managed persistence, and FAISS or QDRANT for self-hosted setups.
There's a library called Mem0 that's gotten a lot of attention for agent memory. What's the approach there?
Mem0 is interesting because it tries to automate the judgment calls about what's worth remembering. Instead of the developer writing extraction logic, Mem0 runs a second LLM call after each conversation turn to identify memory-worthy content. User preferences, stated facts, corrections, important context. It then stores those extracted memories in a vector store and retrieves relevant ones at the start of future conversations. The smart part is the deduplication and contradiction handling. If the user said they prefer Python in conversation 1 and Go in conversation 3, Mem0 detects the contradiction and updates the stored preference rather than keeping both. It also has a graph memory backend in its newer versions, where memories are stored as entities and relationships in a knowledge graph rather than flat vectors, which enables more structured reasoning about relationships between stored facts.
How do you build a persistent user profile with this? Like, an agent that actually knows who it's talking to across sessions.
The pattern is what I'd call a structured extraction loop. After each conversation, run a prompt over the full conversation text. Extract any new facts about the user, their preferences, their expertise level, their stated goals, their previous projects. Format the output as structured JSON. Merge that JSON into a persistent user profile document keyed by user ID, update existing fields, add new ones, flag contradictions for review. At the start of the next conversation, retrieve the user profile and inject the most relevant fields into the system prompt. You don't inject the entire profile. That gets expensive at scale. Instead, embed the current user query, embed each profile field, and retrieve the top 5 most relevant profile facts. A user who's asked a Python question gets their Python expertise level injected. A user asking about team management gets their role and org size injected. The profile exists completely. Only the relevant slice is activated.
What about remembering the outcomes of past actions? An agent that learns from its mistakes over time.
This is procedural memory, and it's the hardest type to implement well. The basic pattern: after each agent run, score the outcome. Did the tool call succeed? Did the user express satisfaction? Did the agent loop unnecessarily? Store the action sequence, the context it was used in, and the outcome score as an episodic memory. When facing a similar task in the future, retrieve similar past attempts, especially successful ones, and use them as few-shot examples in the prompt. What you're effectively doing is building a case-based reasoning system on top of your LLM. The agent doesn't update its weights based on experience, but it updates its effective behavior by retrieving and conditioning on relevant past experience. More sophisticated implementations use this data to fine-tune the model periodically on successful trajectories, a process sometimes called agent distillation. But for most production use cases, retrieval-augmented procedural memory is sufficient and doesn't require the complexity of online learning.
What about the flip side, forgetting? Are there cases where you want an agent to forget things?
Absolutely, and this is an under-discussed part of memory system design. Memories become stale. A user's tech stack from 6 months ago may be irrelevant now. Contradictory memories accumulate and confuse retrieval. And there are privacy and compliance requirements. GDPR right to erasure means your memory system needs to support deleting all data for a given user on request. The practical approaches: time waiting and retrieval. Newer memories get a boost in the similarity search, so recent information naturally surfaces above stale information. Explicit TTLs, memories of a certain type, expire after a defined period. Contradiction detection: when a new memory directly contradicts an existing one, the existing one is archived rather than kept active. And user-controlled memory give users the ability to see, edit, and delete their stored memories. That last one is both a product feature and a compliance requirement if you're operating in Europe.
LangChain released something called LangMem. How does that fit in?
LangMem is LangChain's official memory abstraction layer, designed to work natively with LangGraph. It provides a standard interface for all 4 memory types and handles the plumbing: embedding, storage, retrieval, injection, deduplication. The key design decision is that LangMem treats memory as a first-class citizen of the agent state graph. Rather than bolting memory on as a pre-processing step, memory retrieval and storage are explicit nodes in the LangGraph graph. That gives you full observability over what's being retrieved and stored, and lets you put business logic around memory operations. For example, requiring human approval before storing a new long-term preference. For teams already building on LangGraph, LangMem is the natural choice. For teams building on other frameworks, Mem0 has SDKs for most popular platforms and is framework agnostic.
What does a production memory system actually look like at scale? Say, for a product with tens of thousands of daily active users.
At that scale, a few architectural decisions become critical. First, separate your hot and cold memory. Hot memory is recent conversations and actively relevant profile data. This lives in RDS or a fast vector store with low latency. Cold memory is historical data, rarely retrieved episodes. This lives in cheaper storage like Postgres or S3-backed vector indexes. A router in front decides which tier to hit based on how recent the memory is. Second, async memory writes. Don't block the user's response on memory storage. After you send the response, kick off an async job that does the extraction, embedding, and storage. Third, memory quotas per user. Without limits, power users accumulate thousands of memories, which slows retrieval and inflates storage costs. Set a cap, say 500 memories per user, and use importance scoring to decide which memories to evict when the cap is hit. Fourth, monitoring. Track retrieval hit rates. What percentage of agent calls retrieve at least one relevant memory? If it's low, your extraction or retrieval logic is the problem. If it's high but user satisfaction is still low, your injection strategy needs work.
3 things to do this week if someone wants to start building agent memory into their system.
First, add semantic memory for user preferences to one existing agent this week. Pick 3 to 5 attributes worth remembering: preferred language, expertise level, stated goals. After each conversation, run a one-shot extraction prompt that outputs structured JSON. Store it in a simple key-value store keyed by user ID. Inject it into your system prompt next session. That's a meaningful improvement with maybe 2 hours of work. Second, add a retrieval step before any long-running task. Before your agent starts a complex multi-step job, retrieve the 5 most similar past tasks from a vector store and include their outcomes in the prompt as few-shot context. You'll see measurably fewer repeated mistakes. Third, implement a memory audit log. Every memory written and retrieved should be logged with a timestamp and the agent session that triggered it. This gives you the visibility you need to debug retrieval quality and catch stale memory problems before users do. The full implementation guide, including code for all 4 memory types, is in our blog post at AmtocSoft.blogspot.com.
Memory is one of those capabilities that completely changes what agents are useful for, from a tool you use once to a system that improves every time it runs. Sam, great breakdown as always. For everyone listening, the blog post has full code samples for vector store memory, user profile extraction, and the async write pattern Sam described. Link in the description. Subscribe on YouTube or wherever you get your podcasts, and if you want to support the show, buymecoffee.com/AmtocSoft. I'm Alex, Sam's been Sam, this is Bot Thoughts. See you in the next one.